Hi friends, in this video we'll discuss about the post processing in the Ansys Fluent. So without going into the CFD post, so we will try to post process entirely in the Ansys Fluent only. So here on the screen you can see a pipe which has one inlet. So this is an inlet. So this is an inlet and this is an outlet. What you can see on the screen, and there is an obstruction here that is placed, and initially it is filled with a certain amount of level of water, and now and the remaining is air, and from the inlet we'll try to give more amount of water into this pipe, and we'll see what is the amount of water that is getting reflected onto this wall and coming back to this location, or the vice versa, or how the counters are there and how the volume fraction is been differing from each time step to time step. Maybe we can take an volume fraction of 0.5 for the water, and we'll see how the isosurface is moving and all the pressure counters, velocity counters, so we can check all the stuff in Ansys Fluent itself. So I've meshed it already. I've taken a simple normal mesh in order for our simulation purpose. I'll just start the simulation now. So I'll try to patch and I'll give boundary conditions, some velocity inlet and pressure outlet. It's a normal thing what we regularly do. Mine is academic version, so I have a limited node count, so I cannot go more than 512,000 node element count. So we need to take, I'm taking here a volume of mixture model. So if I can take mixture model, there will be a slip velocity along the surface. So it's a transient approach where gravity, you can see it is in minus 9.81. So minus 9.81 is our gravity, and you can go to the models, and I'll check on the mixture model here, and with implicit body force activated it stabilizes the equation. So that's the reason why we'll try to activate implicit body forces. And now we can have a sharp displaced or dispersed option. So with these things we can have a good interface between water and air. So click apply, and now we need to import water also into our materials tab. So go to materials tab, double click materials tab, create edit. So now I'll go to Fluent database and I'll drag drop to include water into my simulation. So now I'll go to mixture model with phases. Phase 1 as water liquid. I'll try to enter it as water, and phase 2 as my air. So I'll try to enter it as air. Apply. And now so in the phase interaction, so there is a slip velocity between air and the water, so that is been given by this equation manitoral. And so there's a drag coefficient that has been given by scalar Norman coefficient. So I'll leave it default remaining. Now I'll go to boundary conditions and the inlet velocity. So in the inlet velocity you can enter the velocity of the water only, so there is no air, what I mean to say. So there is only water entering here. So maybe I'll take water as to 1.5 meter per second. Apply, close, and air is 0, so there is no air entering. So you can just check here. Yes, air is 0. And in the outlet condition, so there is a backflow for air only, so there is no backflow for water. So we can take backflow volume fraction of air as completely 1, and there is no water coming when it is a reversal flow at the outlet, so we can take air as 1. Now we can go to methods, and I'll try to select a coupled scheme which is much more stable, and have a higher order relaxation terms, so that my scheme will be much more stable. Then I'll go to initialization and I'll try to initialize. So here the entire air fraction is having 0. So now we need to create a region in order to patch the water. So first go to automatic, click, and the cell registers new, select region. In the region you can just select the hex. The hex, it will ask for x minimum, x maximum, y minimum, y maximum, z minimum, z maximum. So here we need to play with z, y minimum and y maximum only. So here we can just check here. Maybe z we can give a random value -10 and +10. It will not bother you that much. This also -10 and +10. but why you need to have a certain value. So why we can just check here. So why this radius is 4 mm. So here in the y negative direction -4, positive direction -4. So negative direction it is -4. So we will enter -4. The two it is in mm. So this is 0.004, and here it is minus 0.001. So it means 3 mm is completely filled with water. So in order to do that, I'm just checking here. Here you check. Next, close it. Next, okay, cancel. Now here we're entering entire air as one. Initialize, and after that you select that air, and for that region there is no air. It is only water. So pass that. Now you can go to the graphics and check for the counters how exactly it looks like. You can just select this and go to the faces and check for water. You can see here completely bottom is filled with water, and here as inlet there is no only water, so it was showing in red in color. So I think is okay. So now we can also have an adaptive refinement also. We'll just try to show how to do the adaptive refinement. First, for that purpose, you can just go to mixture model and use the volume of fluid simplicity scheme, apply. So I'm just using this volume of fluid advantage for adaptive refinement. So in the predefined criteria, go to volume of fluid. Okay. So in the general adaptation, so you need to select here refine option, right? In the general adaptation control, refinement level should be 2, and the maximum element count is 512,000 nodes, so it should not cross that. And yes, just give it as 1, because if it count which crosses, then again it's an headache for us. So the maximum minimum cell orthogonal quality I'm keeping it at 0.05, and adapt, close. Now again you can go to multi-phase. Next, activate the mixture model, so it will not create any problem to you. So that is the way, like, in order to use the advantage of having a already present controls in order to use that. So we have used it, and then you can go to this counters, and this is volume fraction. So I'll give VOF, save display, right, close. Next, I can select other one, and I'll try to give a velocity. So I'll select a plane, and the two, it should cut in between the things. I think it's, yeah, it cut in between. So I'll try to create that plane, close it, and here this is the plane on which I need to know the velocity. Okay, so the mixed velocity I will take, compute display. Right now there is no velocity, so that's the reason why it was showing no velocity. Next, close. So they rename it as velocity. It's a velocity, save display, right? And we'll also check the mesh how it is getting varied. So edges. So you can just check this plane, save display. So you can just check here, this is the interface what is present. So that should also be it will also get refined as we progress. So we'll just check all those things. Now I need to create a scene in order to have the mesh along with our so I'll also create another mesh so that it will show all the things at a stretch. Select these, excluding plane, excluding edges, save display, right? So this is other way of showing. So this is the mesh 2, and now I'll go to scene, new. In this I will try to select velocity, which is having no transparency, but mesh 2 is having transparency, and I'll use this active scene or display state, sorry, it will disable front faces and all the stuff. It's not required, keep it none. And you can just see save display. So now you can see transparent mesh, right, with the velocity plane present inside. So now you can just save, and now we'll try to create another scene which has a volume fraction with mesh, new VOF with mesh 2, again the same method. So we'll try to So we can see that mesh how it has been moving. So now we can go to the calculation activities, solution animation. For every, for two time steps, maybe we'll save scene to use active view. So the view what is present on the screen will be coming into the animation. Next, select for another animation, that is scene one. Similarly, two steps. Similarly, we have that active view, right? So that is a view one. Okay. So now we'll try to run this. Maybe we'll try to select another animation also. This we'll try to have the mesh one as our animation. Okay. Now we'll try to run the thing. We'll select a lower time step, giving a mesh count. We'll just check how is all the convergence and all the stuff initially. Yeah, so I've ran through few iterations. So now you can see the animations. I'll just go to the animations, playback, and you can select animation one, and I'll click on this option so that you will see how the water has been is flowed. So you can see the water is flowing and increasing the level as it is going on, and it is raising it, and it was there in impulsion, so there is a projection. So everything you can see here. Similarly, you can select the velocity and you can check how the velocity. So this is the velocity of the total mixture model, how it has been increasing gradually with respect to the time. So you can see, and finally there is a reflection after hitting the wall, so that also you can see. Maybe I can show you a counter which will be much more apt in order to check the velocity. So you can just check this velocity, compute, display, and that too for water you can just check. Sorry, phase. Forgot to say this is phase, and you can see. So the water is ejecting from this. It's coming, it's hitting, and it's again getting reflected. So now you can see the reflected portion, how the water is been getting reflected. And if you want to check the iso surface of the water, so then you need to go to this surfaces, right click, new iso surface, and you can name this as an iso surface water, and I'll select the phase fraction of water, and that too I want to select zero point 0.5, and I want it for the entire from zone. So you can just create, and you can go to the counter and select the isosurface water with the velocity as its counter. So you can just check. So this is the isosurface of the water, how exactly it is for the zero point 0.5 fraction, and with the velocity. I think you can remove this auto range and keep normal range so that you'll be more uh, visually effective. So you can see the water is injecting or getting reflected, and you can see the water has an isosurface of the zero point 0.5 fraction, where it is the interface between air and the water, right? And you can also check the path lines. So you can go to the path lines, and in the path lines you can select this inlet, and you can also have this mesh highlighted, and maybe you can just make this mesh transparent. So you can select these and display, and remove all the stuff, and lighting also, and the transparency, and click on apply. So you can see this transparency, right? And so apply, close, and you can go to the path lines, and now you can select this inlet, how exactly those path lines are getting distributed. So compute, display. So these are the path lines, how are they getting distributed. And I'll just draw the mesh also, and you can see the path lines are getting tracked by just clicking on this pulse option. You can just see how the path lines are going, coming down due to gravity, and it's after reflecting it's going up, and you can see that is again deflected. It's hitting the wall, some are going into the outlet, some are getting again deflected, right? So if you want to select the entire plane instead of inlet, so that will give a different view altogether. So now again you just check the pulse option on the entire plane, how it is getting varied. You can just check so the particles or the path lines, how they are getting rejected, how they are getting moved, so into the entire distribution, how they are been hitting the walls and all the stuff. And now if you want to have a surface onto which it is getting injected, select, go to this oil flow. So what are all the water particles that is coming from inlet and coming onto the zone of wall obstruct? If you want to have only those particles, you can just click up and then pulse it. So release from surface inlet, and maybe it's not sufficient, so we can select this also. Stop this, compute, save display, pulse. Okay, so that size we need to also enhance. Okay, as well as a plane 6 also we can increase this. Yeah, so I've increased the step size. um, then I'll just pulse it. You can just check which are going and hitting onto this. I'll just stop now and I'll just check only wall obstruction. Yeah, so I'll just pulse it now. So these are the particles coming from the plane and getting injected onto the wall obstruction. So you can see these vortices. So it is rotating. So this is the wall surface vortices what are being getting hit onto the obstruction surface. So this is one type of finding particles ejecting from any of the inlet and outlet or any plane and getting hitting onto a particular zone. If you want to identify, yes, this will be much more helpful to you to identify, right? So this is one kind of post processing what you can browse, and other the particle tracks. If you have any injections, you can use this. And if you want to have any animations, that you can also use this calculation activity solution animations. Or if you want to have the velocity vectors, so you can select the plane and you can just check the velocity vectors. So it is the arrows are getting arranged by with respect to the size of this. So instead of clicking on that, we'll just remove this, sorry, you just customize the vector, this one. So X component, Z component, everything is getting scalar with respect to the velocity components. So instead of that, we can also use this Q criteria normalized, or this says how randomly it is getting distributed. So those Q criterias also you can use as velocity vector for the custom vector 0. So you can just compute display. Now we can see this Q criteria. So these are all the Q criteria what you are able to see. So this gives a randomness, or instead of having that auto range, you can just get to 1 meter per second. And okay, sorry, I'm just clicking on this save display. No, still, yeah. So you can just see. So mostly everything is getting focused on 0.4. I'll just increase the scale to 3, so the size will be much more predominant or much more visually you can see. Now we can see, so the velocity Q criteria vectors, which indicates a distribution or randomness inside the domain. So this is one way how you can represent the vectors. So now we have covered about the counters, vectors, path lines, isosurfaces, animations, and mostly we have covered all the post processing in the Fluent. So I hope guys this video helped you on understanding the most of the post processing in Fluent. Please do subscribe the video and like, share, and share among your friends. Thank you.